This will be the second part of the lecture over the problems that are missed on the Registry Review Exam 1. We'll go over step by step how to look at these particular problems and what to do. So the next one here, and again, these problems are not necessarily occurring in this order if you go through and try to work them. So these problems will come up whenever you encounter them. I can try and fix that, but for now, this is how things are set up. So we've got a treatment of 137 monitor units, requires that a blocking tray factor of 0.963 be included in the calculation. So what are the correct treatment monitor units if the tray is added? This is also going to be part of the MU calculation where you have dose, and then you have the calibration factor times the collimator, phantom scatter. You'll have a wedge factor, tray factor, and then any sort of off-axis factor times. Usually it'll be end up being a TMR, so on and so forth. So in this particular case, all we're going to do is we've got our monitor unit calculation here, and all of these other factors have already been decided, except now we have to include a 0.963. So what we're going to do is, since this has not yet been included in the calculation here, and it should have been, then what we're going to do is we're going to end up taking 137 MU, and we're going to have to divide it by 0.963. Now, you might be thinking, well, we have to go through and we'll have to know the dose or anything and be able to help solve for this. But in this particular case, all we would have to do would be to take the MUs, which have been calculated, assuming that that particular factor was actually just, tray factor. The tray factor was equal to 1. That is not the case. So the number of MUs will have to be increased because the blocking tray factor is actually going to reduce the amount of dose that's actually going to hit the target. So we're going to have to take the number of monitor units in this case and pump them up by a factor in order to be able to get the correct number of monitor units. And as it turns out, if I take 137 and divide that by 0.963, then I come up with 142.2, which and you can see here that that is the correct answer. So that's how that particular problem works out. So let me go ahead and clear off all of this. We'll move on to the next one. A patient is accidentally treated at 78 CMSSD as opposed to 80. The treatment field, the treatment depth is 3 cm. If the prescribed tumor dose is 200 through a single field, what did the tumor actually receive? So in this particular case, you can see here, the answer is going to be 210. The question is, how did they get to it? So the prescribed dose here is going to be 200 centigrade. That's what it should have gotten, and it should have been treated at 80. The problem is it was treated at 78. The question is, how does this affect the dose? Now, the treatment depth didn't change, so we're okay there. Question is, how did this change? In this particular case, the dose that was delivered. I'm going to go ahead and represent this as the new dose as opposed to the old, which in this case is going to be 200. So I'll just write this. And in this particular case, we know that the new SSD is actually going to be here, and then the old SSD is going to be here. We also know that this has to be squared, and this is because of the inverse square law. So what we end up with here is the new dose, or the actual dose, is going to be 200 centigrade multiplied by 80 cm divided by 78. The actual dose should be higher, and the reason is that you are treating at a smaller SSD than what it was actually planned for. So this dose is actually going to go up. That's part of the inverse square law. So all that said, if I take the calculator here, out, so I've got 80 divided by 78, and that's squared, and multiply that by 200. So we end up with 210. And in fact, that's the answer. So this is just an application of the inverse square law. Okay. Had the SSD on that one been further away, then the dose should have ended up being less. So here we have a patient that was treated with a 20 cm long field and a 15 cm long field, and this is matched. Both fields are set at 80 SSD. What is the gap on the skin that the fields are to be matched at 10 cm depth? So let's kind of draw out exactly what this is. We haven't really done a gap calculation here. All right, so we've got somebody here who's lying on the table. And we have our first field here, and that field is going to be 20 cm long. We also have another field here. It's going to pick up where that one left off. Goes over here, and that's going to be 15 cm. So we got 20 here, and we got 15, and all of these are going to be matched at a depth of 10 cm. So they're all coming in from diverging fields like that. Now, if they're going to be matching on the skin, or in other words, right out here, there's actually going to be a small little gap here. Question is, how do we get to that? Well, what we're going to do is we're going to draw the central axis on both of these. So we got the central axis here, and we got the central axis here. Now, why did I do this? We're going to take this measurement right here of the entire length of the field, and we're going to cut it in half. So we're going to be interested in just this segment right here. Same thing applies over here. We're just going to take just that segment. So 15, we cut that in half, and we end up with 7.5 cm. So now that we've taken the lengths of both of those and cut them in half, we need to figure out exactly how much each one of them is shrinking there at the gap. So the question is, how do we do that? Well, we were treating at 80 SSD. if we are treating at 80 SSD, then the gap, or we're not only treating at that, but these fields are matched at 10 cm deeper than that. So if we look inside the patient, once again, let me draw the patient a little bit bigger here. So we know that the field is going out here to 80 cm SSD, but it's also going in a little bit further. That's another 10 cm here. So these fields, these lengths that we see here are actually going to take place at 90 cm into the patient. If we're interested in what is actually being done at 80 cm, we're going to see these fields shrink a little bit. So how does the mathematics of this work out? Well, I know that at 10 cm, that this is a reflection of the length at 90 centimeters deep. The question is, what am I looking at when it's 80? Well, as it turns out, the ratios here are going to be pretty much the same. 10 cm at 90 is going to be the same thing at some value at 80 cm. It also means that I can take a proportion here. 80 divided by 90. That means that X is going to end up equaling. You might be asking yourself, why isn't this kind of stuff squared? The reason this stuff is not squared is because we are dealing with lengths. We are not dealing with area in which things spread out in 2 dimensions. So we're not interested in that. So if I take 10, multiply by 80, divide the result by 90, I get 8.88 or around 8.9. Where am I getting there? So then for the other side there, I see that 7.5 cm over some value is the same at 90 cm divided by 80 cm. X is equal to 7.5 cm multiplied by 80 cm over 90 cm. So I get about 6.7 cm. Okay. So now that I've got this and this, I can figure out what the gap is by adding these two things together and subtracting it from the sum of the 10 and the 7.5. So if I take 10 and add 7.5, that would be the length of everything put together at 90 cm. If I subtract 8.9 and subtract 6.7, come up with a gap here of about 1.9. Okay, that does not look right. Oh, I think I read this question incorrectly. Okay, let's start this again. Let's take this, clear all that out. Well, fields are set at that. What is the gap on the scheme if the fields are to be matched at 10 cm depth? Okay, I think I read the question wrong. Okay, so we got dude here. And we've got this set over here. So we got 20 and 15. I don't think it's worded very well here, but I think what this was meant to be was actually that this is now 80 cm when it's 10 cm deep in the patient, which means that the distance from here to here is actually going to be 70 cm. Let's try that. If I take 20, I'm sorry, not 20, 10 cm, multiply that by 70 over 80. What do I come up with? Ah, okay. Sorry, I don't think that question is read or written very clearly. And so I would like to clarify this question. I'm going to clear out everything here. So I'm going to take 7.5 multiplied by 70 divided by 80. 6.5 to 6.5625. Okay. Same thing still applies though, as far as taking the difference between them. So I'm going to take 10, add 7.5, subtract 8.75, and subtract 6.5625. Read my chicken scratch. And you come up with 2.1875. Okay, so in this particular case, the separation or the gap is equal to 2.1875 cm. Okay, so the moral of this particular story is, in this particular case, it says both fields are set at 80. What is the gap on the skin if the fields are to be matched at 10 cm depth? And what I'm going to do on this particular question, just to try to keep it clear, is to say, if they're mentioned this makes the new SSD, or this makes the new SSD become 70 cm. That way, maybe it'll be a little bit more clear as to what's going on there. So that's my apologies on that. I'm sorry. Right, so the patient is treated with an 8 by 15 cm field, cobalt 60 unit, 80 cm SSD to a depth of 78.5 PDD. What is the percentage depth of dose, or what would it be if the SSD was changed to 100? This is a classic case of using the Maynard F factor. The Maynard F factor is what's going to change the PDD for this particular setup when it's changing from 80 to 100, because you're going to keep all of the same field size, you're going to keep the same energy, you're going to keep the same depth. So the Maynard F factor is what's applied to help with that. So doing the Maynard F factor here, if there are many different ways that this is written, stick with this. And this is what we're going to use in order to compute it. So in this particular case, we have, let's just say the SSD, the SSD1 is going to be equal to 80. The SSD2, which is what it's moving to, is going to be 100. So this is going to be 100. Now, when they're telling you it's a cobalt unit 0.5 is going to be your Dmax. So this ends up being 100.5 times 80. Then over here, it'll be 85 over 105. So we should end up here. Clear everything out. 100.5 divided by 80.5. The result will be squared, multiplied by 85 squared, divided by 105 squared. Okay, so 1.021. Now, how do we go about using this? Well, we know what the Maynard F factor is now. What we're going to do in order to be able to change the PDD is we're going to take the PDD old one, multiply it by the Maynard F factor, and that becomes the PDD of the new one. So the old PDD is 78.5. We're going to multiply that by 1.021. And let's see what we come up with. 80.18. Closest thing to that is going to be the 80.1 here, which I think should be 80.2. Okay, let's keep going. All right. Collimators on a linear accelerator are calibrated for distance of 100 cm. So in other words, whenever we have a collimator setting at 100 cm, that's what we're going to end up seeing. So to obtain a field size of 30 by 30 at 80, what collimator setting is required? In other words, what am I going to tell the system? Again, this is a question of geometry. And so the question here is going to be, okay, I'm going to call this here 80 cm away, and this is going to be 100 cm here. I know what the length here, this is going to be 30 cm here at 80. Question is, what is this length at 100? We're going to use a similar triangle argument where I know that I've got 30 cm at 80. I don't know how many cm I have at 100. So I know 30 divided by x is going to be equal to 80 over 100. Doing cross multiplication, I come up with x is equal to 30 times 100 over 80. So I come up with 37 and a half. This is what the setting would be at 100. And since we're looking at 30 by 30, we here would end up with 37 and a half by 37 and a half. So that's where that comes from. Okay, move on to the next one. So a dose of 3000 centigrade is delivered to a depth of 8 cm at PDD 76%. What is the dose to an underlying organ at 14 cm at a PDD of 58%? So I want you to follow my lead on this one. First of all, I think this looks a little funky there. I don't like the way that looks. So let's type that in. Okay. Save that. Okay. So since we have 3000 that's being delivered to a depth of 8 cm at PDD of 76, we know that at this particular point that the dose here of 3000 centigrade divided by 0.76 is going to end up equaling the dose at D max. Why is that important? This is going to be my reference value that I will use for a later computation there for the PDD at the new point. So 3000 times 0.76. $39.47.37. So that's the dose of D max. Now, the question is, what is the dose at 14 cm? Okay, so that means basically 3,947.37 centigrade multiplied by, oh, what's the number here? 58%. Okay. As it turns out, that's our answer. There we go. So in a problem like this, what we're doing is we're trying to figure out how the dose at one particular PDD relates to the D max. And then once we have it at the D max, we can then turn around and then figure out what it is at a different point. So that's where that comes from. Okay, this one's going to be tricky. So we're going to assume a half value layer of lead is equal to 3 millimeters. How thick would the lead have to be to reduce exposure of 100 milliroentgens at 4 meters to 100 milliroentgens at 1 meter? So what we need to do here is we need to try to figure out exactly how to calibrate this particular measurement to see what dose is being delivered at 1 meter, and then how does that compare with what we want to see. So if you'll remember the old exposure rate formulas, let's see, I thought I had the here. Okay. Dose rates are inversely proportional to the distance squared. So whatever your intensity here is, whatever the dose rate is, it's equal to some sort of constant divided by the distance squared. Now we're going to take advantage of that here. Oops, there we go. So let's take a look here and say, okay, I know I have an intensity 100 milliroentgen, and this is at a distance 4 meters. What's going to be my new intensity when the distance is shrunk to 1 meter? So I know I2 divided by I1 should be equal to, let's see if I put this over here. And I believe it is D1 squared over D2 squared. So the intent, since we're getting closer, that would mean this would be true. So in this particular case, the original intensity is this multiplied by 4 over 1 quantity squared. So this is equal to 100 milliroentgens times 16, or in this case, 1600 milliroentgens. So that's what's going on currently. We want to see, we want to go from 1600 milliroentgens, and I'll just put this as a 3. I want to see that drop. Oops. See that drop to 100 milliroentgens. So the question is, what sort of factor do we need to apply here in order to get to that? Well, this is a half value layer. It is a half value layer, which means if we take 1600 millirankins, multiply that by 1/2 raised to some power, which I do not know what that power is, and eventually it'll come down to 100 millirankins. I'm not exactly sure what that is, but if I try to solve for n here, then I can come up with the answer. How do I solve for n? Well, I'm going to divide both sides by 1600 millirankins. That gives me 1/2 n equal to 100 divided by 1600, which is 1/16. If I take the natural log of both of sides, then what this says is that I have the natural log of 1/2 raised to the n power is equal to the natural log of 1/16. And as it turns out, there's a property of logarithms in which I can move that exponent down to become a coefficient. That leaves me with a natural log, or n times, I'm going to get my act together here. So n times a natural log of 1/2 is equal to the natural log of 1/16. That means that n is equal to the natural log of 1/16 to the natural log of 1/2. So if I go, sorry for the mess, 1 divided by 16 is equal to this. Take the natural log, divide that by 0.5 natural log, come up with 4. Now, you might be thinking to yourself, great, 4 isn't listed as one of the answers here. That's right. What this number does tell me is how many half value layers I have to apply in order to be able to reduce the air exposure down to that point. Since I have to apply 4 of these half value layers, which is essentially what that is telling me is how many half value layers I can reduce it from this to this, then I take 4 of these values of 3 millimeters, which basically means if I take, I'm going to write over here, if I take 4 times 3 millimeters, I come up with 12 millimeters, which is what I have to apply in order to be able to get the exposure down to that point. So that was a tough one. That was a longer problem that we had to go through. So now let's move on. We're going to go here and calculate the monitor units to deliver 200 centigrade to the 90% isodose line using 12 MeV electrons at 100 SSD. If the measured output for the cone and cutout is 0.787 at this value. Now, what we're going to do is I want you to take a quick look at this and see that it's about 282. So if I take this, if I take our dose that we want to deliver and divide it by 0.787, I want to show you what we got. And again, we haven't covered electrons yet, so. So we had 254. That's not quite this. What did we leave out? What is it that we needed to change? This would work just fine if we took the electrons and just went to the 100% line. This particular case, we're going to the 90% line. So there's something else that we have to do here. So rather than just go with a 787, we also have to multiply that by the isodose line. It's down there, which is 0.9. So because of that, I have to go here and I have to divide this again by 0.9. That's where we get the 282. So I want you to be aware that that's what we have to do here. So 282 monitor units. That's where it comes from. So patient is receiving 300 centigrade per day to a spinal cord lesion at 89.5% depth dose. What is the daily given dose at Dmax? Now, I want you to, and I just messed it up. Oh, no, I was right. Given dose. Given dose is going to be equal to the tumor dose, or the Dmax dose, divided by the PDD. So in this particular case, what we're going to do is we're going to take, we're going to take the tumor dose, which in this case is going to be 300 centigrade, and we're going to multiply it by the PDD. So the given dose you come up with 268.5. Or 269 in this particular case. So I want you to be aware of that particular definition of given dose. So all of the following data was obtained using a 15 by 15 cm field size at 100 SAD. Dose of Dmax in the tissue is 280. The backscatter factor is 1.031, and the TMR at a depth of 12 is 0.721. So find the dose delivered at 12 cm depth through a single 15 by 15 field at 100 SAD. So the SAD is going to be fine. That doesn't change. So how do we determine this? Well, we've got our phantom here. We're going to be hitting a particular target, which is 12 cm deep. And our distance over to here is going to be 100 cm SAD. Okay. So now we know what the dose is that we want to deliver here, or we know what the dose is at Dmax, sorry. What we need to figure out from all of this information is how to get from the dose at Dmax to the dose that's delivered here. Well, how do we get the dose that's delivered here? We'll call this Dmax. How do we get to that particular point? Well, we know at this particular point here that the backscatter factor here is 1.031. We know that the TMR at a depth of 12 is going to be 0.721. Question is, what is it that we need out of this in order to be able to find the answer? Matter of fact, what is the answer? Let's take a look here. 202. So let's take a look here and let's take, what is it, 280? Whoops. Take 280 and divide it by 0.721. What do we get? Sorry, I did that wrong. 280 and multiply it by 0.721. Come up with 201.88. Do we need the backscatter factor at this particular time? We don't really need it. It's kind of thrown in there to kind of throw you off guard. If all we had was an exposure in air to some point here, that would be the equivalent of D max here. At that particular point, then we would need the backscatter factor to go from air into the tissue and then from the tissue out to this particular depth. But in this particular case, we already have the dose at D max. We don't really need to use the backscatter factor. So in this case, all we really needed was the TMR. Okay, so now we've got the PDD for a 12 by 12 field, 6 MV, 5 cm depth at 80. SSD is 82.8%. Calculate the percent depth dose for the same field size and depth for 100 cm SSD. Well, that sounds like a pretty familiar question, right? And it's because we've already worked this except for a cobalt unit. So here, if we go through and we make the adjustments, and rather than use the Dmax for cobalt, we're actually going to use it here for 6MV. So again, our Maynard F factor here is going to be SSD2 plus Dmax divided by SSD1 plus Dmax. All this chunk gets squared. And then over here, we've got SSD1 plus D over SSD2 plus D squared. That becomes the new SSD, which I'm going to go ahead and write over here. SSD1 is equal to 80 cm. SSD2 is going to be 100 cm. Okay, so let's see what these values are. So 100 plus 1.5, is that divided by 81.5? When you add those together, you square it, you end up with something that's close to 1.55. So I'm going to write that down. Times. And this is going to be 85 divided by 105 squared. As it turns out, Maynard's F factor here. 1.016. This is what we'll end up multiplying the old PDD by. To get to the new one. So I'm going to take that, multiply it by the old one, which is 82.8, 84.16, or 84.2. Okay, calculate the dose at D max if 200 centigrade is delivered to 7 cm below the skin at the 72% depth dose. So what do we come up with? Let's see. We know that the D max here is going to be 200 centigrade. We know that it's going to be delivered the dose we want to deliver. Oh, I'm sorry. That's my bad here. As you can see, the answer here is going to be 278. This is what's being delivered here at 7 cm. So we're going to take 200 centigrade and divide it by 0.72. So we end up with something close to 278. Which is what we get. Okay, so we got a few more to go here, not too bad. Collimator setting is 8x10 on a 100 SAD machine. The SSD on the patient's skin reads 90. What is the field size on the patient's skin? Again, this is one of these similar triangle problems where we've got, I'm not going to draw my other patient. It looked pretty bad the last time we did this. Let's see. So I've got, and I'm just going to do this in one dimension. So here, since the SSD is 90 and the SAD is going to be 100, that means this is going to be 10 cm depth, which means we're going to end up with something that's 8 cm at 100 SS or SAD. The question is, what is it right here on the skin when that is at 90 cm? So again, we've got 8 cm, which is equal to 100 cm. These are similar triangle arguments. X is what we have here at 90. So that means that whatever the size here is at 90 is going to be 80. I'm sorry, 8. There we go. Sorry. 8 times 90 divided by 100. So we end up with 7.2. Same thing goes with the 10 cm field. we're going to use the same thing there. And I'll just call that direction or that variable y. So y is going to end up equaling 10 cm times 90 over 100. So the new field size should be 7.2 cm by 9 cm. Which indeed it is. So treatment designed to be given at 100 SSD is mistakenly given at 94. What is the error in dose? This is going to be a problem concerning the inverse square law. The inverse square law is, whatever dose you're delivering here is going to be changed due to how close you are to the target. In this particular case, you're going to end up, since you are closer than what you were before, than what it was planned for, this is what you're going to end up with. So you've got dose times, and it's 100 over 94. Now, if you were further away, then you would end up underdosing. So if I take 100 divided by 94 and square that, then you got 1.13. And this right here is what they're referring to. And again, this comes straight out of the inverse square law, where the dose is going to be proportional to the SSD squared. So in this particular case, we end up with a factor here of 1.13, which means we end up with all the dose that we had before plus 13% more. This, whatever falls over here on the right side, tells you this is the percentage that is going to be the overdose, since you have something that is in the one, that is 1 here on the left side of the decimal point. Okay, localization of film is not something that we have looked at specifically in this course yet. So let's take a look at it here. Localization film was taken at 109 FFD, focus to film distance. A 3.5 magnification ring was placed on the patient's skin. It measures 4.2 cm of the film. What distance is the magnification ring from the focal spot? So, start off here, you've got your focal spot. Branches out from here. Strikes patient here. And then you've got the size of the ring here, and then you've got the film out here. That ring has a certain dimension, a certain size. Once we know that, and we know how big it appears on the film, then we can gauge how far it is away if we know the distance from here to here. So we know the distance from here to here, and that's going to be 109 cm. We don't know what the distance is from here to here. That's what we're trying to find out. We know that this is 3.5 cm. We also know that the distance or the dimensions of the ring out here, which is a little bit larger, is going to be 4.2. So we know that the ring is 3.5 cm at a certain distance. We don't know yet what that distance is, which we're trying to find out. We know that it's 4.2 cm at 109. So X is going to be equal to 109, sorry, no decimal there, 109 cm multiplied by 3.5 cm divided by 4.2 cm. This is all linear because we're looking at distances at that, and we're not trying to square the area, square the result, because it's not obeying the inverse square law, because it's not spreading out in all directions, just spreading out in one specific direction. So I take 1.09, or not 1.09, 109. Okay, let's try this again. 109. Multiplying that by 3.5 divided by 4.2. And we come up with 90.83. So that distance is what it takes to go from the focal spot out here to the ring. Oops. Okay, got 1, 2, 3, 4, 5 more problems to work here. Okay, so a dose of 200 centigrade is to be delivered at a depth of 10 cm at 100 SAD. From a single 15 by 15 field with 6 MV X-rays. Given the information below, what would the treatment monitor units be? Okay, so we've been handed a TMR, we've been handed the output in air, we've been handed a backscatter factor, and we've been handed a PDD. We're not going to use the PDD. And the reason is that this is an SAD setup. Because it's an SAD setup, that means that we've got phantom here. This is Dmax. This is the point of interest out here at 10 cm. So how do we, if this is the only information that we're given and we know we want to deliver 200 here, question is, how do we come up with the monitor units? Well, better field, it's coming through and interacting here. The way we get to it is that we have our measurement in space to get our output in air. We're going to then translate it from air to the tumor, or to the phantom by using the backscatter factor. That tells us what the dose would actually be at Dmax. In order to get the dose from Dmax down to a particular depth, that's where we're going to use the TMR. That's what the TMR is used for. So in this particular case, we know that the 200 centigrade is going to be delivered at 10 cm depth. That means that we have to take the output factor So we're going to be using that. We're going to have to multiply that by the backscatter factor, 1.044, in order to be able to get the dose from air into the dose at Dmax. And then we have to multiply that by the TMR, which is 0.806, and that gets us the dose at a specific depth. So we got a lot of factors here that we're going to be multiplying by. So we've got here 1.015. We're going to multiply that by 1.044. And we're going to multiply that by 0.806. Sorry, 0.806. Take the reciprocal of that, multiply it by 200, and we come up with 234, which is in fact exactly what we need. So again, in this particular case, we're going to be looking at the dose at whatever the depth is going to be equal to our calibration factor multiplied by the backscatter factor multiplied by the TMR. That gets us from space into the phantom at Dmax, and then from the Dmax down to another point downstream. Since this is not an SSD setup, we will not be using the PDD. A 3.5 cm block on a blocking tray 45 cm from the source will block what width at 100 cm? Okay, this is another one of these where we're drawing it out, kind of gets us an idea here. So I'm going to put this out here. We got our phantom right here. And let's say the entire distance here that we run is going to be 100 cm. The blocking tray is set at 45, so it's set right about there, 45 cm. So there's a block in here, and I'm just going to put it on this side to kind of help with things. That side there is going to be 3.5 cm. The question is, how much does it block over here? This is another similar triangle argument. So we've got 3.5 cm that is blocking, or that is the measurement of 45 cm. We have some other length over here, which we don't know what this new blocking length is, but we know it is at 100 cm. If we take X, put it over here, the cross multiplication, that gives us 3.5 cm times 100 cm divided by 45 cm. So we come up with 7.777. So that gives us 7.78 cm. Which in fact is the answer. Okay, so if a patient receives a tumor dose of 250 centigrade per day at the 79.2% depth dose, what is the daily maximum subcutaneous dose? This is a matter of scaling the dose that we are getting. So the tumor, if we're basically the maximum subcutaneous dose, this is also referring pretty much to the Dmax. Skin is usually defined as going about 5 millimeters below the skin. it's not the same with every particular energy, but shooting for the Dmax is usually what we end up doing to try to get an idea. Although nowadays, once you contour in the skin or whatnot, you can just see the information off the DVH. So we've got 250 centigrade divided by 0.792. So we end up 315.65 or 316. It's essentially what we got here. Okay. So a patient's prescription requires a total of 180 centigrade to be delivered per day to equally weighted parallel opposed fields, POP, parallel opposed. The treatment time to deliver 100 centigrade is going to be 2.15 minutes. What treatment time must be delivered to each field following the prescription? So this is 1.94. So we know proportionally that it's going to take for 180 centigrade, we know it's going to take 2.15 minutes. Now, seeing as how we, sorry, that's not right. We know it for 100 centigrade, it's going to take 2.15 minutes. The question is what time is going to be delivered if it's going to be parallel opposed fields? Well, the entire treatment is going to deliver 180 centigrade, but we have two fields that are going to deliver each part of the prescription. So really what we are looking at here is just delivering 90. So we've got 90 centigrade here, and we have no idea how long that's going to take. So I'm going to cross multiply, which puts the X over here, and then all of this other garbage moves over here to the other side. So X is equal to 90 centigrade over 100 centigrade multiplied by 2.15 minutes. Those two cancel. X is equal to what? $1.935 minutes. Or 1.94 minutes. So a patient is treated on a 6 MV linear accelerator. The patient is set up to 94 cm SSD. Tissue to air ratio at 6 cm depth is 0.87. And the output at isocenter in air is 1.02 centigrade per monitor unit for the required field size. How many monitor units will it take to deliver 100 centigrade to that depth? Well, let's try. Go. We know we want to deliver 100 centigrade to that depth. We know that the output in air is going to be 1.02 centigrade per monitor unit. We also know here that the TAR at this is going to be 0.87. So we're going to put that in here. Now, the TAR is what's going to let us get from the dose in air to the dose in the phantom at that particular depth, and that's what we're looking for. So we should end up here with 100 divided by, and I don't think I wrote that right. Hang on. Yeah, I didn't do that right. Let's see. There we go. My bad. Divided by 1.02, and we're also going to divide that by 0.87. So we end up with 112.68, which is 113. Okay. I hope this gives you at least some idea as to how these answers are generated. If you have any questions over anything like this, please don't hesitate to ask, and we'll do this again the next time that we have a mock registry.